Today we shall learn about nature of equilibrium, phase rule and Newton's theorem, VLE quantitative behavior and simple models for VLE and dew point and bubble point calculations using Raoult's law, VLE by modified Raoult's law and dew point and bubble point calculations by using modified Raoult's law. Before going to the contents, what is the background of this unit? However, composition changes are the desired outcome of the chemical reactions and of industrially important mass transfer operations. Processes such as distillation, absorption and extraction bring phases of different composition into contact. And when the phases are not in equilibrium, mass transfer between the phases alters their compositions. Both the extent of change and the rate of transfer depend on the departure of the system from equilibrium. Thus, for quantitative treatment of mass transfer, the equilibrium temperature and pressure and phase compositions must be known. The most commonly used coexisting phases in industrial practices are vapor-liquid equilibrium, liquid-liquid equilibrium and liquid-solid equilibrium and vapor-solid equilibriums. Now we are going to discuss about vapor-liquid equilibrium, that is unit 3. Now we will discuss about nature of equilibrium. What is equilibrium? Equilibrium is a static condition in which no changes occur in the macroscopic properties of a system with time. Macroscopic means bigger system. Example, consider an isolated system which consisting of liquid and vapor phases. Both phases reaches a final state wherein no tendency exists for change to occur with the system. Here, the temperature, pressure and phase composition reaches final values. After reaching final state, there is no change in the values of temperature, pressure and phase compositions. After that, they are fixed. Now coming to microscopic level. At microscopic level, conditions are not static. That means varying the conditions. But level of varying is very minute. Molecules with higher velocities near the interface overcome surface forces and pass into the other phase. But the average rate of passage of molecules is the same in both directions, this direction and this directions. And no net interface transfer of material occurs. That means in both the directions are same. That is negligible one. So no net interface transfer of material occurs. There are 4 measures of composition. How to measure the composition? We have 4 measures of composition. First one is mass fraction. Mass fraction is defined as the ratio of the mass of a particular chemical species in a mixture or solution to the total mass of mixture or solution. Mathematically, mass fraction is indicated with Xn, which is equals to mi by m or mi dot by m dot. I means individual species. Here, mi is the mass of ith species and m is the total mass of the mixture or solution. Now coming to second measures of composition is mole fraction. The mole fraction is defined as the ratio of the number of moles of a particular chemical species in a mixture or solution to the number of moles of mixture or solution, which is represented as xi is equals to ni by n or ni dot by n dot. Here Ni is the number of moles of ith species and N is the number of moles of the mixture. Now coming to third measure of composition is molar concentration. Molar concentration is defined as the ratio of the mole fraction of a particular chemical species in a mixture or solution to the molar volume of a mixture or solution. Therefore, Ca is equals to Xi by V. That is equals to Ni dot by Q. Here, Ni dot is the molar flow rate. Q is the volumetric flow rate. Xi is the mole fraction of individual species. V is the volume. Now coming to fourth measures of composition, that is molar mass of the mixture or solution. The mole fraction weighted sum of the molar masses of all species present. That is sum of the product of the mole fraction multiplied with individual mass of the species. That is equals to sigma xi mi. Now coming to phase rule, Duham's theorem. We learned about phase rule in CET1 is theoretical only. Here we have to develop phase rule mathematical form based on the principles of solution thermodynamics and phase equilibrium criteria. In this one, we have to consider a non-reactant system which is at equilibrium, which contains pi number of phases, each phase containing n independent chemical species. The degrees of freedom is defined as the number of phase rule variables which must be arbitrarily defined in order to fix the intensive state of a system at equilibrium. The number of phase rule variables which must be arbitrarily specified in order to fix the intensive state of a system at equilibrium is called as degrees of freedom. Simply, the degrees of freedom is the difference between phase rule variables and number of independent equations. For the system of interest, here the above terms are as follows. The first one is total number of phase rule intensive variables T comma P and n minus 1 species mole fractions for each of the 5 phases. Therefore, phase rule variables are 2 plus n minus 1 into pi. Here 2 is the temperature and pressure. N minus 1 is the mole fractions for pi number of phases. The masses of the phases are not phase rule variables. So here we are not considering the mass of the phase because they have no influence on the intensive state of the system. Here mass is independent. So the masses of the phases are not phase rule variable. Now the number of independent phase equilibrium equations connecting intensive variables for each of the n species are pi minus 1 into n. The difference between the number of phase rule variables and the number of independent equations connecting the phases is the number of variables that may be independently fixed, which is called as degrees of freedom. Therefore, degrees of freedom is equals to 2 plus n minus 1 into pi, which is number of phase rule variables minus number of independent equations, which is pi minus 1 into n. That is equals to 2 minus pi plus n. Here, the state of a system is said to be completely determined. When the system is completely determined and which is characterized not only by the 2 plus n minus 1 into pi intensive phase rule variables, but also by pi extensive variables represented by the mass of the phases, then only we have to said to be completely characterized that system. The total number of variables is equals to 2 plus n minus 1 into pi plus pi. Here pi is the extensive variables. Therefore 2 plus n pi. Previously we are writing the phase rule for an open system. Here we have to consider a closed system. Closed system means there is no mass in or mass out. If the system is closed and formed from specified amounts of the chemical species present. Specified means mass is defined. Specified amounts of the chemical species present. Then material balance equation we have to write for n species. Pi minus 1 into n phase equilibrium equations provide a total number of independent equations, which is equal to pi minus 1 into n plus n. We have to write pi minus 1 into n equations for n species. That's why we have to add n also, which is equals to n pi. Therefore, the degrees of freedom is equals to difference between the total number of variables and number of equations. That is equals to 2 plus n pi minus n pi. That is equals to 2. Now coming to Duhamel's theorem. Duhamel's theorem is another rule similar to phase rule. Duhamel's theorem and phase rule are both are similar ones. On the basis of the above result, that is degrees of freedom is equals to 2. Duhamel's theorem stated as, the statement of Duhamel's theorem is, for any closed system formed initially from given masses of prescribed chemical species, the equilibrium state is completely determined when any two independent variables are fixed. This is the statement of Duhamel's theorem. For any closed system formed initially from given masses of prescribed chemical species, the equilibrium state is completely determined when any two independent variables are fixed. Duhamel's theorem applies to closed systems. The systems are at equilibrium. The extensive state and intensive state of systems are fixed. Then only we have to apply Duhamel's theorem. That is, F is equals to 2 plus n pi minus pi n, which is equals to 2. Number of variables minus number of equations. Therefore, degrees of freedom is equals to number of variables minus number of equations. That is, 2 plus n pi minus pi n is equals to 2. N pi gets cancelled. However, the number of independent intensive variables is given by the phase rule. Therefore, it follows that when f is equals to 1, at least we have to specify one of the two variables. Therefore, it follows that When f is equals to 1, at least one of the two variables must be extensive. If f is equals to 0, both variables are extensive. The minimum number of degrees of freedom for any system is 0. If f is equals to 0, the system is invariant system. Therefore, substitute f is equals to 0 in phase rule. That is equals to f is equals to 2 minus pi plus n. Therefore, 0 is equals to 2 minus pi plus n. Therefore, pi is equals to 2 plus n. Pi is the maximum number of phases which can coexist at equilibrium for the system containing n chemical species. When n is equals to 1, pi is equals to 3, which is the characteristic of triple point. If pi is equals to 3, that means 3 phases coexist at equilibrium. That point is called as triple point. At triple point, the 3 phases, that is gas, liquid, solid phases, coexist in equilibrium. When f is equals to 1, then the system is called as univariant system. When f is equals to 2, system is called as divariant system. Now we have to solve one problem on phase rule. Calculate the degrees of freedom when liquid water in equilibrium with its vapor. Here, number of phases are liquid phase and vapor phase. Therefore, pi is equals to 2. Here, pi is equals to number of phases, n is equals to number of components. F is equals to 2 minus pi plus n. Here n is equals to 1, pi is equals to 2. Therefore, f is equals to 2 minus 2 plus 1, which is equals to 1. If f is equals to 1, the system is univariant system. Coming to second bit. Here, liquid water in equilibrium with a mixture of water vapor and nitrogen. Here, number of components are 2. That is water and nitrogen. The number of phases are water, that is liquid, and vapor phase. Liquid water and vapor, that is liquid phase and vapor phase. Number of phases is equals to 2. Number of components is equals to 2. Degrees of freedom is equals to 2 minus 2 plus 2 is equals to 2. If f is equals to 2, then the system is called as divariant system. Now coming to third bit. A liquid solution of alcohol in water in equilibrium with its vapor. Here, alcohol is one component, water is one component. Number of components n is equals to 2. Here, number of phases also 2, liquid phase and vapor phase. Therefore, f is equals to 2 minus 2 plus 2 is equals to, if f is equals to 2, that is degrees of freedom is equals to 2, then the system is called as divariant system.